Hello, hello. Let me know if you can hear me clearly, and then we'll get started. Type in anything into the chat. Perfect. All right, so the file has just been posted because I've been literally trying to put things together in the last 3 hours. So this is what I could get together in the last 3 hours. So it's a little bit shorter than I would like it to be, but I got a lot of the main ideas put into this practice exam. So tomorrow night, I'm hoping we can get a few more problems squeezed in than what I have here, maybe somewhere around like more than 20, whereas here there's 16 of them. So, but yeah, you can go ahead and download that if you haven't already. It's on the front page on Canvas. 17 problems on here. So, and they're all multiple choice. And then we'll get started here in a few more seconds. So again, it's on the front page on Canvas. Freshly posted within the last 15 minutes. All right, let's get started on this. Hello. So, let's see here. Let's take a look at this first problem. Let me know if the video quality looks good, if you can read anything I have here, so you know. Let me know if that looks okay, and then we'll go from there. So. Okay, so this first problem here, we have two slits. So we have monochromatic green light with the wavelength given, shines onto two slits, and the pattern is observed on a wall. The light going from each of the two slits takes a different path to the same location along the wall. So in other words, so you have the two slits kind of pictured here in the figure, and you have a bunch of spots along the wall or the viewing screen, and these two slits will have light passing out of them, and now the light is going to be spread everywhere through this entire setup. However, we're interested in the idea that the light will take one path from one of the slits, like let's say from this slit here, the top, to some, perhaps it might be a bright spot, maybe it's a dark spot, we don't know, but it goes to a particular spot in the wall. And the other source of light from the other slit reaches the same exact spot of interest. So what happens is there's two different paths taken to the same location, and that path length will be slightly different. So given that one of the paths is 1250 nanometers longer than the other path, and the central bright spot is defined as the 0th bright spot, what do we observe where the two paths meet? So let me sketch this out a little bit better off to the side. So you have two slits. Okay, so here's the two slits here. And there's a viewing screen over here. And you have this pattern of bright, dark, and bright, dark, bright, dark. Let's use this. Okay. So here's your interference pattern along the viewing screen or the wall. Now, what I'm saying is that there is a particular spot of interest along the viewing screen. So let's just say that my spot of interest is, right here. Okay. So there's this location along the wall. I don't know where it is exactly, but I do know that there's two different paths that have to be taken to reach that same spot along the wall, whatever spot that is. So there's going to be some distance for this path on the top, and there's going to be some distance for the path on the bottom, which are slightly different than each other. The only thing you do know is that one of these paths has an extra length of 1,250 nanometers. So given that your wavelength of light in this problem is, I believe we have 500 nanometers. 500 nanometers. And given that the difference in the length of the path, if I call this length L1 and let's call this length L2, so we have two different lengths, the difference in those two lengths, L2 minus L1, is 1250 nanometers. Given this information, I need to figure out what spot on the wall I'm looking at. And I'm going to tell you in this problem that's either going to be a bright spot or it's going to be a dark spot. So how do we figure out exactly if it's going to be a bright spot or a dark spot, and how do we figure out which one it is? So the thing is that if you remember conceptually that the bright and dark fringes that are seen are determined by constructive and destructive interference, then you can figure out what the significance of this extra distance is. So, for instance, if I were talking about the center bright spot, then the two paths would be symmetrical to the center. So in other words, the distance traveled by each path to the center bright spot is the same distance, or in other words, there's no difference in the distance. So we get constructive interference when that extra distance is a multiple of the wavelength, or there is no difference. So if I were to go to the next bright spot or the bright spot after that, it would be an extra wavelength or two extra wavelengths, three extra wavelengths, and that's where the M value comes from. So for all the dark spots, it's going to be half of an extra wavelength, 1.5, 2.5, 3.5. So what I'm saying in here is that if we have this extra distance, it turns out that 1250 is really 1,000 nanometers plus an additional 250 nanometers. The 1,000 nanometers is two whole wavelengths. So given that you have two waves approaching the spot, and they are just some number of wavelengths off of each other, it's constructive interference. So this is just 2 lambda. That would have been constructive if it were just that. However, we don't have just that. It's plus 250, which is half of a wavelength. So it's plus an extra half a wavelength. So in other words, this is destructive. Now, we know it's got to be a dark spot, but now which one it is? Now, if you were to just pull the lambda out of here, this equals 2.5 times lambda. Okay? This is your M effective value, 2.5. So for instance, from the center, the first dark fringe is half of an extra wavelength, 0.5. The next dark fringe would be 1.5. And the third dark fringe would be 2.5 extra wavelengths. So we know that, therefore, this is the third dark fringe. This can be possibly a little bit more confusing. So if you have any questions on how I arrived at this conclusion, let me know in the chat and we'll go from there. I wouldn't call it rounding. I guess you could round to get the answer in this case. It's not rounding necessarily. It's more about realizing that, okay, so let me do this in a different color. So the center here, the center bright spot is m equals 0. Okay, that means we have no path difference at all. The two paths from the two slits are symmetrical to the center, so they have the same distance to that center bright spot. So there's no extra distance, and therefore there's no extra number of wavelengths that fit in. But then for each successive bright spot, you get one extra wavelength in the path difference. 1 lambda, 2 lambda, 3 lambda for all the bright spots. So you get m equals 1, 2, and 3. For all the dark spots, it's everything in between. So all I'm saying here is that for this first dark spot, because we know it's a dark spot, it has to be half of wavelength out of phase with the other path. So the m value is effectively a half. So given that it's effectively a half, and we know that each successive one will be an extra wavelength, the second dark spot will be m equals 1.5 effectively. So it's one wavelength plus an extra half, which makes it destructive. And then the next one is m equals 2.5. So you count 1 dark fringe, 2 dark fringes, 3 dark fringes. So that's how we arrive at the conclusion that it's the third dark fringe in that case, which you could round it in this case, but I guess depending on how you do it, rounding may not be the answer to this. It just happens in this case that you can round it and it ends up being the correct answer for that. So, two-part question. Do we check to see how many times lambda divides into the path difference in order to see how many wavelengths we have? And if it doesn't divide evenly, will it be destructive? That is correct. So in other words, if you took the path difference of 1250 and you divided it by, you divide that by 500, you're going to get 2.5 out of that. If it's a whole number, it's constructive because you can fit an even integer number of wavelengths into it, so it arrives constructively. If you get a half integer, then it's destructive. So you can pretty easily figure out if it's constructive or destructive by just seeing if it's a whole number or if it's a half integer. But I guess figuring out if it's the second or the third dark fringe requires just a little bit more thought beyond that. So no problem. All right, let's take a look at the next one. 2. Monochromatic light with a wavelength of 600 nanometers shines through 2 slits which are separated by a distance of 50 micrometers and projected onto a wall which is 100 centimeters away. What distance from the center of the pattern is the 4th dark fringe? I want the distance from the center. So we're measuring some distance in meters ideally. And this is a double slit problem. So let's rewrite this. So the double slit, this is problem 2. So for the first one, the answer was third dark, so that would have been E. This one, problem 2, is also a double slit. Okay. There's the 2 slits. Here's the viewing screen. And we're going to be paying attention to the 4th dark fringe from the center. So from the center, here where you have your central bright spot, you're going to count 1 dark fringe, 2, 3, and there's a 4th one somewhere out here. So this is the 4th dark spot. However, we know that the effective m value is not going to be a whole number for this. It's going to be a half integer. So from your m equals 0 bright spot, you know the first dark spot has to be a half of an extra wavelength. So your m equals 0.5 effectively. You count the dark spots away from the center You increment by 1, so it's 1.5 for the M value for the next one, 2.5, and finally the fourth dark spot is effectively 3.5. Okay. So remember that's going to be your M effective value, and we'll take a look at that, how that's used in the equation. Now, we have a couple things we can set up. So for instance, in this picture, you could draw the line of sight from the center to the point of interest, and it creates this right triangle that gives you an angle theta from there, and that gives you a distance y along the viewing screen, always measured from the center. So you have the central bright spot, and you measure a distance y to whatever point of interest along the viewing screen you have. So we know we can apply a couple of equations here. So you can either do one of the following. You can either A, so let's say option 1, you can use d sine theta equal to m lambda to try and solve this. Normally this equation was used only for bright spots or for constructive interference. However, this equation can technically be used for the dark spots too, so as long as you use the effective M value. In other words, the fourth dark fringe is M 3.5. So you can do this as long as you plug in 3.5 here. The other option, option 2, is to use the modified equation which accounts for the destructive. Specifically, it would be written as d sine theta is equal to m minus a half lambda. So if you use it this way, then you have to make sure the stuff in the parenthesis turns out to be 3.5. So it doesn't really matter what it says inside the parenthesis, it only matters what the value overall in the parenthesis ended up being. So for instance, if I use this equation here, I would use m 3.5, okay, in the top equation. If I use the bottom equation for the dark spot, the parenthesis needs to end up being 3.5, so in other words, in here, m minus a half needs to be equal to 3.5, and to which you would say the m value, so therefore m would have to be 4 in that case. Okay. So you can kind of see how it really doesn't matter which way you go about it, as long as you are effectively saying that you have half of an extra wavelength somehow. Whether if it means taking m equal to 4 for the fourth dark spot and subtracting a half to get 3.5, or taking the simpler equation and just dropping 3.5 in it to begin with. It doesn't really matter how you do it. Now, regardless of which route you take, we need to solve for what distance from the center we need. So the distance from the center is y. We need the equation that says tangent theta equals y over L, in which we could solve for y, but we know that according to the small angle approximation, we can take tangent of theta and we can replace it into sine of theta. So in other words, tangent of theta is approximately equal to sine of theta, so that we can take, I'll do it in the top equation in my case. I prefer just using the top equation. I'm going to take the equation here, and I'm going to drop this into here, so I'll drop the y over L in place of sine of theta. So in other words, we have that this implies d times, so replace sine of theta with y over L, and that's equal to m lambda. We're going to solve for y here, so solving for y, we get that y equals, that's going to be multiplied by L, so we get m lambda L, and then we're going to divide off by d. Okay, so m lambda L over d. That'll solve for y. We take and plug in the appropriate values forget this. Keeping in mind that we're treating m as in this equation, so it's going to be 3.5. So we say that y equals 3.5 for the effective m value. The wavelength is given in this problem as 600 nanometers. So 600 times 10 to the minus 9th meters. The distance L to the viewing screen or the wall in this problem is 100 centimeters, so exactly 1 meter away. So we use 1 meter. All divided by the distance between the two slits, which is given as 50 times 10 to the minus 6th meters. In other words, 50 micrometers. You put this all in, and you get y equals. So let's calculate that real quick. 50, 10 to the minus 6th, the bottom. Flip it, 3.5, 600, 10 to the minus 9th, and 1, we don't include that. So 4.2 times 10 to the minus 2, which means it's 4.2 centimeters. So it's 4.2 centimeters. That's our y value. So the answer for this is B. Let's see, what questions do we have? Does that approximation of sine theta and tangent theta work all the time with double slits? In this class, yes. This approximation right here will always work as long as the angle is small, and that's always assumed in this class at least. Small angles normally mean something less than 10 degrees, but that's pretty much everything we're doing, so I wouldn't really concern about it. But yeah, you can apply this approximation in all your double slit problems, unless stated otherwise, basically. Let's see. Apparently something crashed. Hopefully it's good now. Looks like everything got better. So, any other questions on any of this for problem 2? Especially relating to the equations and how you use them, in case that was confusing, but hopefully it was clear enough. Question 2 is bueno. Okay. Sounds good. All right, so let's take a look at the next one then. So 3. You have monochromatic light. There's a wavelength 700 nanometers that shines through the two slits, so it's another double slit. And a bright spot on the viewing screen is observed to be 10 centimeters away from the center. If the wavelength of light is halved, what distance will the bright spot be away from the center if the wavelength is halved? So this is a problem where you have two situations or two scenarios, and you're simply just comparing the two scenarios. So as you do something to one thing, what's going to happen to the other thing? So in here, let's see, what do we want to do? Let's take that, and let's do that. Actually, let me go back to this real quick. Okay. I hate it when I lose my eraser. There we go. All right. So I only give you very limited information in this, and that's because you just need to figure out what happens if you cut the wavelength in half. So for this one, double slits, we're going to use the same equation, and we're going to make the same approximation. So I'm going to cut straight to one of the later steps, which is that under the approximation, d times y over L is approximately m lambda. And I'm going to say it's, again, m effective. Now, I tell you that the distance along the viewing screen from the center to whatever spot of interest it is, it doesn't really matter in this case. The distance along the viewing screen is y, and I tell you it's 10 centimeters. Now, I take the wavelength to be 700 nanometers, and I'm just going to cut it in half. So I want to know what happens to the value of y as a result of cutting the wavelength in half. So for that, all you do is you take the equation, solve it for what you need, which is in this case y. So in other words, y is approximately equal to m lambda L over d. And you just write their proportionality. In other words, you ignore all the things that stay constant. So this implies y is proportional to. So things that do not change in the problem from one situation to the other include m. The m value is constant. We're watching a particular spot on the pattern shift. So the m is constant. The wavelength is not constant, so you do write that. So lambda. The length L to the viewing screen from the slits stays constant in the problem. The distance between the slits, d, also stays constant in the problem. So in other words, in this problem, y is only proportional to the wavelength. It's only based on changing the wavelength in this particular problem. So all you do is you plug in the factor by which you're changing the wavelength by, which in this case, you're cutting it in half. So by cutting it in half, you would say, okay, you just plug in a half, and that's all there is to it. So in other words, you get a half for the y value. So this is a way of saying, therefore, y after is half of y before. So if the y value before was 10 centimeters, we take half of 10 centimeters, and we get 5 centimeters. So this is the result of cutting our wavelength in half. So you don't need to manipulate and plug in everything into your equations. You can just take the equation and then figure out if you cut this in half, then that has to be cut in half. And it doesn't have to be just one factor only. I'm only doing it with one factor, but you could change multiple things at the same time. So for instance, I could also cut in half the length L. And what would happen is that 1/2 from the length L would combine with your 1/2 from your wavelength, and you would get 1/4 out of that. That's all that would happen. So you only consider things that change in your problem as part of that proportionality. So let me know if you have any questions on this, and we'll take a look at the next one. Um, 10 centimeters is your y value. So a bright spot on the viewing screen is observed to be 10 centimeters away from the center. So your y value. Yeah. So likewise, if the problem said, if the wavelength is doubled, then y equals 20 centimeters, that's correct. Also, feel free to answer each other's questions if you think you have the right idea. Right. All right, so let's take a look at number 4. A single 25 micrometer wide slit is illuminated with monochromatic light. So this is a single slit problem. Produces a pattern on the wall which is 1.5 meters away from the slit. The width of this central bright spot is measured to be 10 centimeters. So how wide is it along the viewing screen, which has to do with your distance y, but it may not be the value of y. What is the wavelength of the light in this setup? So for the single slit problem, so for the last problem, the answer was C. So answer is C for the last problem. So single slit here and a diffraction pattern on here. Keep in mind on the single slit problems, the center bright spot is wider than any of the other bright spots on the viewing screen. So the other bright spots on the screen are smaller in width than that center one. So that's only for the single slit. Now, remember in the single slit problems that you are not counting bright spots, you're counting dark spots as whole numbers. So the first dark spot is M1, and then M2, etc. Now, I'm telling you that in this problem, let's straighten this out a little bit. In this problem, so here's your center, I'm telling you that the central bright spot has a width of 10 centimeters from end to end. So remember that any information pertaining to the bright spot in a single slit problem has to be translated into dark spot information. So in other words, 10 centimeters across this bright spot in the center from end to end is actually the distance between the surrounding dark spots. So you have a dark spot here, m equals 1, and another m equals 1 dark spot on the other side. This distance is 10 centimeters. But that's not my y value because my y value is always measured with respect to the center. So with respect to the center, given that the pattern is symmetric, my y value is actually 5 centimeters. So I'm going to say that y is actually 5 centimeters. And with my single slit setup, I have that w, the width of the slit, sine of theta equals m lambda, where m is the dark spot count. So 1, 2, 3, 4 dark spots, etc. So here, since we are looking at the first order dark spot, on either side we use m equals 1. We need to solve for, in this case, we want the wavelength of the light, so we need to solve for lambda. We're also going to substitute the sine of theta with the approximation, which is sine of theta equals tangent theta, which is y over L. So w times y over L is approximately m lambda. We solve for the wavelength. So the wavelength, we divide by m to the other side, so w times y in the top divided by m times L in the bottom. We have the slit width, so that's going to be 25 micrometers, 25 10 to the minus 6th meters. The y value is 5 centimeters to either side, so 5 times 10 to the minus 2 meters. Your m value is 1 to the first dark fringe, and your L, the distance from the slit to the viewing screen in this problem, is 1.5 meters. So wavelength equals, we're going to calculate that out to be, so 25 times 5 is 125 divided by 1.5. And then the powers of 10, so we have times 10 to the minus 8th in the top. So we get, I think in this one, is that 8.33? 10 to the minus 7th meters? I think that is. So in other words, the wavelength equals 800, and it's closest to 835 actually. So it's approximately 835 nanometers. Okay. Might want to check my math at any point during this, just in case I accidentally plug in something wrong, but it should be 835 nanometers. The reason why I say that is because when I made this problem, I actually think I got a different number than this, so you can double check if I got that, if you get the same answer as me. But yeah, because it's got to be 125 for that, divided by 1.5, so it's got to be around that number. Are there any questions related to, perhaps why you're cutting the distance in half? Anything in this problem? How do you know which m value to use? In other words, why do you use m equals 1 specifically? Because when you're doing this, okay, so actually I think I can answer two questions at once, because the other question is, why do you cut y in half? So I'm going to tie those questions together. So you cut your setup in half every single time you do this, regardless, because everything's measured with respect to the center. So I tell you that the bright spot is 10 centimeters wide from end to end, and we remembered that the bright spot is just going to end where the dark spot is. So what I'm really telling you is it's 10 centimeters from dark spot m equals 1 on one side to the other m equals 1 dark spot on the other side. Now, when you do this, this is equivalent to saying that you cut it in half and you use the line of sight to that dark spot, which makes this right triangle here. The distance y is along this side of the triangle here alongside the viewing screen, which only it goes to the center. So the y value, since it's measured to the center, has to mean that you're cutting this distance in half to get that half there. Now, as you use this though, you know that when you solve this setup, if I were to ask you what is the y value to the m equals 1 dark spot, you would know that it's 5 centimeters in this case. So likewise, if I'm telling you that it's 5 centimeters from the center to that first dark spot, you know it has to be the m equals 1. So it has nothing to do with the fact that there's two dark spots, and it has more to do with what that line of sight is to whatever point of interest it is along the viewing screen on one side. You don't even care about the other side symmetrically. So hopefully that answers that. Let me know if that sounds good, and then we'll move on. You're welcome. Anytime. So number 4, we have that it's closest to actually 835. I'm actually really glad I made that option, because I think when I did this problem, I got like 1670, but it's actually 835 here, so I'm glad I made that answer. Number 5, suppose that the width of a single slit setup was decreased. So the width of the slit is decreased. Which of the following could happen as a result of that? 4 options. The diffraction pattern would shrink, the wavelength of light decreases, and the distance to the viewing screen decreases, or all of the above. So take 30 seconds, think about it for yourself, and then shout out an answer if you have one. You don't have to explain anything, you can just give me the letter. D, I think. Don't we all? Any other thoughts on this one? D? Okay. A? Okay, so finally some split. So let's think about this for a moment. Now, it's a single slit setup, so you know which equation belongs to it. It's the one we just used. W sine theta equals m lambda, and you're going to replace sine of theta with y over L. So we have the same equation. Now, let me write that equation out here so we can see what we're looking at. So, let me jump to what the approximation says, is that W times y over L is approximately m lambda after you make the small angle approximation. Now, I want to know which of the following could happen as a result of changing the width of the slit. So now I'm decreasing the width of the slit, so I am changing this value here. Bringing that value down, decreasing it. How will that affect other things in the equation? So now, in order for the equation to remain equal, you can do one of the following things. You could perhaps, if W is decreasing, you could decrease the wavelength. That's a possibility. Now, especially if you move the stuff to the other side, let's do that actually. The width is m lambda L over y. Okay. So how could I get my width to decrease? So it would either correspond to a decrease in the wavelength, a decrease in the distance between the viewing screen and the slits, or an increase in the y value. In other words, the pattern expands along the wall. So now the thing is, though, is that in a particular setup, there are certain things you're keeping constant. In other words, you have the same setup where I'm telling you that there's a single slit and the viewing screen is some distance away. And we're not changing that in the problem. So just because you change the width of the slit in the problem, it shouldn't change, for instance, your distance to your viewing screen, because I never told you that you were going to change that. Or perhaps, let's say that I illuminate the slit with green light, right? Why would changing the width of my slit change the color of the light that I'm shining onto it, if that makes sense? So just because the equation is telling me that, you know, I could use these things to calculate the width of the slit, it doesn't mean that changing the width of the slit will change the color of the light. It doesn't really make sense. So really, answer is B, the wavelength of light decreases. And the answer is C, the distance to the viewing screen decreases. Those things are constant in the problem. They do not change just because I'm changing the width of the slit, which is actually why I threw in the answer all of the above, because I figured you might use the equation a little too much to look into that. Those things are fixed in the problem. They never change as a result of changing your slit width. So the only answer left is A, but I think I've actually done it the opposite way, because you change the width of the slit by decreasing it, actually would expand it. So I'm going to say, pretend A has the word expand here, not shrink. I meant to say expand for that. So the answer for this is actually just A. The pattern would expand. So let me write that off to the side here. So pattern would expand. Okay, and this is because you notice that as you decrease the width of the slit down, the only way that's going to work out in this equation is if the y value to any particular spot on your pattern goes up. In other words, it gets further from the center, so it expands away from the center. So it expands, not shrink. All right. So with that wording difference, the answer is A, change it to expand. Yeah, B and C are not true because those things remain fixed in the problem. I never change the distance to my viewing screen. That's set in stone. The wavelength or the color of the light is set in stone. Neither of those would change just because I'm changing the width of my slit. Especially look at the wording here. Which of the following could happen as a result? So does changing the width of the slit cause your wavelength to change or cause your viewing screen distance to change automatically? Those things are untouched. The only thing that in this set of information that has the ability to change as a result is what happens in your diffraction pattern. So the size of it, does it contract inwards or does it shrink, or I'm sorry, does it expand outwards? Y is always, always, always the distance along your viewing screen. Take a little tape measure or something like that. Here, let me do this. Okay. Okay, so the top, here's the top view. Okay. This is the typical view that we draw. You have your slits over here and you have your viewing screen over here. Okay. And whatever number of slits you have over here, it doesn't matter if it's single, double, or if it's a diffraction grating. This is the top view, okay? So in the top view, from the center to any spot you want to investigate is the distance y, okay? That's y. It's always with respect to the center, okay? But let's say if you do a side view, okay? If I show the viewing screen on the side view, I'll see something like this. This is my screen. Here's a bright spot, dark spot, bright spot, dark spot, bright spot, and symmetrical. Okay. This one is the center. Okay. So here's the viewing screen here. Let's pretend that where you're sitting, is where the slits are. Okay. So just so you can kind of get a feel for this three-dimensionally. So pretend that you are the slits and pretend that this is the viewing screen, okay? So if I were to take this, measuring device, this tape measure in this case, and I were to stick the tape measure out to you, the viewer, okay? That's where the slits are. That is the distance L in your problem, okay? Now, the viewing screen itself, if this is the viewing screen, my tape measure goes from the center to any spot elsewhere. So if I want the distance to my second bright fringe, that's my Y value right there, always from the center. So hopefully that makes a little bit more sense with what those are, but let me know. Hopefully that made it a little bit more clear. Yes, always from the central. Clearer than the book. I try. Can you explain briefly why it would expand? Okay, so it's based on this equation here. You take your equation that you use for your single slit or your double slit, it doesn't really matter. It would still do the same thing. So you substitute in your small angle approximation and then you either solve it for W or you solve it for Y. It doesn't really matter. So actually, I'll show it solved for Y. The most important idea is that as you do to one side, something has to happen on the other side. So if I solved it for Y instead, Y is approximately, so I would multiply by L and divide by W. Okay. So in here, I'm asking what happens to my Y value as a result of changing any of these. So in that case, your M value doesn't change. The color of the light doesn't change. The length to the viewing screen also doesn't change in the problem. The only thing that does change is the slit width. How big or how wide is the slit? The slit width is decreased, but it's in the denominator. A number getting smaller in the denominator makes the whole fraction larger, so we're saying that the y value increases. So the y value increasing means you take this pattern right here for your viewing screen, and you make a measurement from the center again to, let's say, the second bright spot. So here, the distance between these 2 points is the distance y, for example. If my y value increases, as according to that equation, I would say that this spot would have to move further away from the center. So the y value increases. Okay, so the pattern expands outwards. That's what we're saying. Cool. Let's take a look at the next one. So again, the answer is A, given that you change it to the word expand. That's what happens when I make this in a short time, is I make plenty of mistakes making these. 6. 2 green plants with an overall color corresponding to an approximate wavelength of 550 nanometers are 1,000 meters away from a person whose pupil, in other words, the opening in your eye, the aperture, or if you want to refer to it as a single slit, you can. The pupil is 4 millimeters in diameter. What minimum distance must the two objects be spaced apart so that they can be resolved as two separate objects? Okay, so this word right here already tells you what you're supposed to do with it. However, even without that word, you should recognize that the whole idea of resolution is that you could see two sources of light as two separate things. Okay, so seeing the sources of light as two separate things or two separate objects is the idea of resolution. So for that, in terms of a picture, this is how it looks. So 6. So the top view, your bird's eye view of this, will look like the following, is that there is a person right here. Okay. There's a person at this location here. And somewhere, some distance away, this green marker is not working. Let me grab another green marker. Okay, hopefully this screen works. Okay, we're good. So you have two quote-unquote green objects, and their wavelength is approximately 550 nanometers. These two objects are some distance away from you. Okay? So there's the two green objects, and the distance from you here out to where those two objects are is approximately 1,000 meters, or 1 kilometer. Okay. Now, you have a pupil in your eye which lets light through, so it's just a single opening and it has a diameter. And as the light from the two objects comes toward the pupil, so the light comes towards the pupil like this from both objects. Okay? They both come into the pupil and hit the back of your retina. The details don't matter in this problem, but in case you're interested. The light comes and hits the inside of the eye, and the thing is that based on the ideas of diffraction, okay, so you have a diffraction pattern where there's bright, dark, and bright and dark. Turns out that if the two sources of light are too close to each other, their diffraction patterns overlap so much that they appear as one object. So what I'm saying is there has to be some minimum distance between the two objects, which is actually just analogous to the distance y. So when you're doing a resolution problem, the distance between the two objects is basically treated as the distance y. So again, only for resolution problems. Okay. So now, you treat this like a single slit problem with the following modification. The modification is that instead of it being, so I'll write in parentheses, this is single slit, W sine theta is equal to m lambda. That's the single slit problem. This is really going to become, so we're going to write it as capital D. This is the diameter of the aperture or the opening or your single slit. So it's like your slit width. Sine theta equals 1.22 lambda. Okay? So we're going to use this in this problem. So I just kind of noticed the similarities between the equations. Now, so given that D is defined as the diameter of the opening, or what's also referred to as the aperture. So if you do any photography, it's an aperture. Now, theta in this equation is defined as the angle separating the sources. Okay. So in this case, you have your two sources. There's going to be some angle between those two lines of sight here. That angle is treated as theta. And you can apply the small angle approximation here too. So it actually turns out that using, so if sine of theta approximately equals tangent theta, which can be just set equal to y over L, you can just rewrite this equation as you would for your single or double slit problems with the approximation. So D times y over L is approximately equal to 1.22 lambda. And you can solve for the distance y in here, which is the distance that separates the two sources of light in our case. So y is approximately 1.22 lambda times L divided by the diameter of that opening, which is the pupil. This is going to be 1.22. Let me write it over here. Y is approximately 1.22 lambda, which is given to be 550 nanometers. Times the length L, which is the distance away to the two sources. So this is essentially the L. Notice how similar this is to your single slit problem. So it's 1,000 meters, okay, divided by the diameter of the opening, which is 4 millimeters, 4 times 10 to the minus 3 meters. If you're a little bit more into the workings of the eye, technically the pupil can dilate and it can contract between somewhere around like 2 millimeters and 8 millimeters, depending on what your eye is doing with the light around, so if it's bright or if it's dark outside. So calculate all of this, and you find that it's 4 times 10 minus 3, invert, multiply 1.22, 550, 10 to the minus 9th, and 1,000. Okay, so we get for this one that y equals, let's put this in, because I give it to you in meters, so 0.16. I might be off a decimal place on this. Let's find out. I get 0.17 meters. let me know if you get the same thing. Otherwise, I think the answer choices might be off by a whole decimal place. So let's figure that out. The 1.22 comes from a detail in the formula which is beyond the scope of this class. If you want the details of where the 1.22 comes from, you can look up something called the Airy disk pattern, and it might tell you a little bit more about where the 1.22 comes from. It's also related to something called a Bessel function, which is again beyond the scope of this class. So I can't really explain much other than that it has something to do with where the dark spots overlap where the dark spot overlaps the other dark spot of the other diffraction pattern from the other source. Okay, so we're all getting 0.17 meters, or 0.167 or 168. So I'm afraid that these are all off by a factor of 10, unfortunately. So shift the decimal point over, so it's 0.168, 0.138, etc., etc. The answer should have been A for that one. Yes, it's analogous to the M value being 1.22, but I say that analogy with a big grain of salt. It's kind of like that, but not really. I don't think I could say an answer confidently for that. Any other questions on the resolution problem and how you apply things in the resolution problem? Okay. So the answer was supposed to be A, just shift the decimal place. Number 7, we have white light illuminates diffraction grating. I'll get back to that question in a second. Which produces a spectrum of color on a viewing screen 1.5 meters away, shown below, with the measurements indicated with respect to the center, as always. So for instance here's the center, right? And from that center, you have, so from the center, you have the measurements here. So you have this distance here, and here, and here. That's all the distance from the center. So now, given those measurements, assuming that red and violet light respectively are these two following wavelengths, 700 and 400 nanometers, what is the number of slits per centimeter on the diffraction grating? Let me briefly look at the question that you had before we jump into that. Would there be a question for resolution that we would use 1.22 for M? So it doesn't have to do with using anything for an M value, because there is, we're not going to discuss anything with an M value in it. And the resolution problems will always have the 1.22 characteristic to it. For this problem here, the diffraction grating is treated very similarly to a double slit problem. So you use the double slit equation to solve this. However, there is the additional bit of information that you need to learn how to use, which is the number of slits on the grating per centimeter. So essentially, that piece of information is most related to the distance between the slits for the two slit problem. So how this is done is so problem 7. Where's the blue? Okay. So let's say that let me do this. So I'm gonna blow up the size of the diffraction grating so you can see more of the details. So what I'm doing here is I'm dashing in this, but when I'm dashing in this, what I'm actually drawing is a ton of slits. Okay. So you have a ton of slits here. Now I've only drawn like 10 slits, but I want you to keep in mind that diffraction gratings have thousands of these per centimeter. Okay, so you take literally this much distance between, a couple of your fingers, and there's more than 1,000 of these slits in that small distance. Now, for the sake of understanding this, I've blown this up bigger. Now, let's say that this happens to be, this is a small example. This is not the problem itself, but let's say this is 1 centimeter from here to here, right? What would happen in this problem is, let's say that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, hey, there's actually 10 slits there. What do you know? Now, there's 10 slits there. So what I would say is that in this example that I'm giving you, there will be 10 slits per 1 centimeter. Or in other words, you would take the 10 slits and you would divide it by 1 centimeter, and that gives you 10 slits per centimeter. Or if this distance were 2 centimeters, you would just divide by 2 centimeters and it'll tell you how many slits there are per centimeter. Now, the reason why you need to know this is because it pertains to the information about the distance d, which is the distance between the slits. So in other words, the distance from here to here, let me use a different color. The distance between here, oh, this is the bad one. Let me get that one out. Distance between there and there is d. Between here and here is d. Between here and here is d. And you have basically 10 of those distance d's. Okay. So in order to get the distance d, if you're given how many slits per centimeter, all you do is you flip it. So in other words, d is actually just 1 over 10 slits per centimeter, so that you get 1/10, which is actually 0.1 centimeters per slit. Okay, so this is the distance d if you were to just flip it. So for this particular problem, what I want to then do is figure out what the distance d is, so that if I flip it, I will get the number of slits per centimeter or per meter. So let's find that out. So I'll scale this back down. So you have a diffraction grating, which has just a ton and ton and a ton and ton of slits. And you have some distance to your viewing screen, which is over here, and there's a pattern that's displayed on the screen. Okay, so there's a whole bunch of colors on the viewing screen. Now, briefly describing to you what's actually happening in the problem, why you're seeing all of these colors here, because diffraction gratings will actually separate the multiple colors of light that you have. So white light will separate into a whole spectrum. All you really need to focus on for this problem is realizing that I give you the proper information for the red and the violet wavelengths here. So I give you the wavelengths. And I also give you where the red and where the violets are located in this picture. So with that, all you have to do is pick one and then solve for whatever the distance d is in the problem. What's the distance between the slits? So again, solve it like a double slit problem. So you pick, let's just say red or violet. First person to throw something into the chat, pick red or violet. Someone shout it out. Red. Okay, so red. Now, I can take any red fringe in that picture and treat it like a double slit problem, basically. So let's say if we use red. Okay, wavelength is 700 nanometers. And I can pick any of the red fringes. So for example, now if you notice in the diagram here, I actually have two places I can look at. I could look at the red fringe on the right side over here, which says that it's 3.50 millimeters away from the center. Or I could take the red fringe over here and I can say, oh, it's 7 millimeters away from the center. The difference is this is the first red fringe from the center. It's mirrored on this side. And this one is the second red fringe. So you can choose m equals 1 or you can use m equals 2. It doesn't really matter. However, if you want to reduce the number of calculations you have to make, use m equals 1. So we're going to use the first red fringe and we're going to use y equal to 3.5 millimeters. So now we have that d sine theta is equal to m lambda. We're going to make the approximation. So d times y over L is approximately m lambda. We need to solve for the distance d between the slits. So d is approximately m lambda L over y. We're taking the first red fringe by our choice. It's m equals 1. We're using the wavelength for red by our choice as long as we're consistent. So 700 times 10 to the minus 9th meters times the length to the viewing screen, which in our case, it's 1.5 meters away. So 1.5 meters divided by the distance y from the center to whichever point of interest, which is, in our case, we have 3.5 millimeters to that bright fringe. So 3.5 times 10 to the minus 3 for milli. And we calculate this distance d. We find that the distance d is approximately, so we have 3.5 times 10 to the minus 3 inverted. It's on the bottom, multiply across 700, 10 to the minus 9th, and 1.5. Okay, so we get d is approximately 3 times 10 to the minus 4th meters. So that's our value for d. Now, this is not the answer because this is the distance between the slits. We need how many slits there are per, in our case, we want it per centimeter. Okay, so we need to flip this answer first. So we have that 1 over d equals 3.33 times 10 to the 3 slits per, but now this is in meters, so it's per meter. Okay. If you want to rewrite this, this is actually 3,333 because it's actually repeated slits per meter. Okay. So if I want it per centimeter, I need to say that we have to convert this to centimeters, which actually I can already see I'm not going to get one of the right answers. So, okay, so meters on top. That's what I get for making this in less than 3 hours. Per 100 centimeters. So for this, we divide by 100. We get that it's approximately 33 slits per centimeter. Let me double check my math here. Let me know if you agree with my answers or if you disagree with them, but let's check to make sure that this is what we get. So y is again the distance from the center to whichever point of interest you're trying to investigate. So in other words, we are choosing to use the first red fringe on the right side, which has a y value of 3.5 millimeters given in the problem. So real quickly again here, distance from the center here out to whatever point you choose to investigate, which I tell you that you have multiple options. We're just choosing 3.5 because it's the first red fringe from the center. So y equals 3.5 millimeters. I use 3.5 millimeters, 700 for red, 1.5 meters for the viewing screen. That all looks good. So I think my distance D is fine. If anybody agrees with the distance D, you flip it to get the number of slits per meter because it's in meters. So you get 3,333 slits per meter, but you want it slits per centimeter. So you have to divide by 100 to get it in centimeters. So it's 33 slits per centimeter. Let me know if you disagree with anything that I've done. No one disagrees? Okay. Are there any questions on this problem then? Okay, so the answer is obviously not there then. It's 33. Okay, cool. So the answer's not there. It's 33 slits per centimeter. Okay, let's take a look at the next one. So the main thing that I want you to get out of the diffraction grading problems is that you need to convert between using D and then having slits per meter or slits per centimeter when you do 1 over D, and then convert it as necessary. Number 8, you have a layer of oil that sits on top of a layer of water and is exposed to the atmosphere, so in other words, air. Rays of light reflect off of the top and bottom layers of the oil. Which of the following are true? Circle all that apply. Okay, so all of them that apply. These first two answers relate to the light that reflects off of the top surface, and the last two answers relate to what happens on the bottom surface. So here, this is a thin film problem. Now, technically, we don't even need to consider it as a thin film. We just really need to consider what happens to the light when it reflects off of the surfaces more than anything else. But you can make this into a thin film problem. Now, in these problems where the light reflects off of the surfaces, we have that. Let's say, so here's the layer of oil. This could be any kind of oil, really. And then water beneath. Okay. So you have water under here, and then you have air on top. Now, the idea would be that, so actually here, I think I needed to actually give you in the problem that the oil is an index of refraction which sits between air and water. So I want you to use the following values for this problem. So for these two, you kind of are already familiar with these. Use an index of refraction for this one of 1.27. Something around there. So what I'm saying is that the index of refraction for the oil is somewhere between the index of refraction compared to the index of refraction for air and water. So now, given that we have this order of the indices of refraction, I want to know what happens to the light that enters the system, comes in like that. There's going to be light that reflects off of the top surface. And there's going to be continuing light that goes under into the oil, bounces off the bottom surface, and then comes out like that. Okay, so there's two reflections that occur. So for the reflection that occurs off the top surface, you have to ask, is it going from low to high or high to low, index of refraction? So in this case, we go from, as we go there to there, we go from low to high. So anytime you go from low index to high index, there is a phase shift that occurs in the light itself. So you have light that will have, here's some bunch of waves, and what will happen is, if you have a bunch of beams of light coming in, they could all be in phase like this, so it would be constructive. A phase shift would mean that you take one of these waves and you shift it by some amount. So let's say if you take this wave and you shift it by half of a wavelength. So if you took this and you move it half a wavelength over so it lines up to here, like this. So that would be half a wavelength. By shifting it over half a wavelength, you would end up with the following. These two waves are now destructive. So what happens is when you go from low to high, the light that gets reflected gets shifted by half of an extra wavelength. So in other words, lambda over 2. Like that. Now, on the bottom layer, the other one sees the same thing because the index of refraction for oil is going to be less than the index of refraction for water. So the same shift occurs for the bottom because you're also, again, going from something that's relatively lower to something that's higher. So on the second reflection, you also get a phase shift of lambda over 2. So the following statements that are correct in here include statement A, which says that the light reflecting off of the top surface is shifted by lambda over 2 in phase. The other statement, statement B, is the other case where it's not shifted, so that's not correct. So we have A is one of the correct answers. And C is also correct answer because the light reflecting off of the bottom surface is also reflected by, or shifted by lambda over 2. So when you're doing the thin film problems, you're going to ask this question at some point. When you have the reflection off of the top surface and the reflection off of the bottom surface, you need to consider how much they're shifted by and then what the difference between them is. So for instance, if you have a phase shift of lambda over 2 for the top surface and another phase shift of lambda over 2 for the bottom surface, the difference between them is 0. So when you apply it into this equation, which I will point out, by the way, is not correct on the formula sheet. I already talked to him and he agrees that it's wrong, so pay attention here. Your formula for the thin films should say the following: 2nt over lambda plus this phase shift lambda, phi, equals m. You can either write it this way or you can write it this way. Okay. The way that's probably going to appear on the formula sheet, in our case, is probably going to be this right here. Okay, so I'll tell you how you use that. Now, what I want you to notice here for these phase shifts here, I've said that they're both half of a wavelength. If you ignore the lambda, you get a constant of a half out of them. Okay, so you get a half and you get a half. If you were to look at the difference between them, the difference between them is 0. Okay, there is no difference between them. That difference is what goes into this factor right here, which is pertaining to the phase shift. So this is the relative phase shift here. In our problem, if we were to solve this as a thin film problem, the value for this would have been 0. In other problems, what might happen is the bottom surface does not phase shift, and you might get a 0 there, and you might get that the difference is 1/2, in which case you would plug in a half there. So if you look on the formula sheet, it says use it as 0 or a half. That's what it means for that. I'll incorporate that problem as a problem to do on the second version of the practice exam, so we'll go over that more in the live stream tomorrow night. So let me know if there's any questions relating to either something related to the thin films with this formula, or reflection off of surfaces, and then how you get phase shift or not. What's the symbol in the middle of, for the equation? It's phi. Yeah, it's a capital phi. PHI. It again represents the relative phase shift, so right here. It's defined as the relative phase shift. Okay, so in other words here, in our example, the phase shift on reflection 1, so let's say example, reflection 1 has a phase shift of a half. It's implied that it's half of a wavelength, basically. But phase shift of a half. Reflection 2, the phase shift is also 1/2. So therefore, the relative phase shift is equal to a half minus a half, which is 0. Okay, so that's how you reach that conclusion in this case. So that's how you use it in these problems. So again, like on the formula sheet, you'll see on the side it says that it's equal to 0 or a half, and it basically is referring to this. So in our case, it happened to be 0. But in other problems, the second reflection might be different, so then it might end up being a half, depending on your case. So isn't the N for oil 1.6? It depends on the oil that you have. In some problems, the oil will have a lower index of refraction than the water, but I guess you could make a different oil which has a higher index of refraction. That's a piece of information that you should be given in the problem. So let's assume in this problem that I actually wrote in that the N value was less than the N value for water. That's one of the things that I'll add in the correction. So you're saying if it was from high to low, would the phase shift be a half? So the relative phase shift would be 1/2. So if you had, let's say we use oil being index of refraction of 1.6, which is higher than water. So let's say hypothetically, instead of going from low to high in the bottom part of this, you go from high to low. In that case, you would get, so pay attention to the wording of what I'm saying. So the phase shift that occurs from that reflection when you go from high to low, the phase shift for that is 0. Okay, so you get 0 phase shift for the bottom reflection. Meanwhile, the top reflection is low to high, so you get a phase shift of a half. The relative phase shift between the two would be a half minus 0, which would be a half. So make sure you're distinguishing between what's the phase shift of either of the two reflections and what's the relative phase shift between the two, which is comparing the two values to each other. So if they're the same, then the difference is 0. If they're not the same, then in your cases they'll be ending up as a half. So distinguish between phase shift and relative phase shift. So to rephrase your question, if you asked if the relative phase shift would be 1/2, the answer would have been correct for that circumstance. All right, let's take a look at the next one. Let's transition to doing relativity. It'll go a little bit faster from here, I'm hoping. These, especially the ones at the end, should be a little bit quicker, so we'll hopefully finish by 11. So number 9, an everyday example of relative velocities could be a person walking on a conveyor belt at an airport where the person moves at 5 meters per second relative to the conveyor, and the conveyor moves at 10 meters per second with respect to the ground. As a result, the person would be moving at 15 meters per second with respect to the ground. Now consider that a person rides on a super awesome skateboard, which is capable of traveling with a speed of 0.5 c, in other words, half the speed of light. They shine a flashlight in the direction of motion, so in the direction they're traveling, relative to a person standing on the ground nearby. How fast would the light beam appear to move at? This answer you should be able to figure out almost immediately. What is the answer to that? There's only 2 answers that you should be getting here. Yeah, it's still just C. No matter what perspective you view it from, something can only still be traveling the speed of light at maximum, and that's light itself, something that doesn't have mass. So the answer is C. It'd still be just the speed of light. Now, in this problem, I could have done something else, such as not use a beam of light. I could have said the person has their skateboard moving at 0.5 c, and something on the skateboard could be, thrown at like 0.7 c. And then you could add the velocities together in that special way, which actually I'll write down here briefly. So there is a relative addition of velocities equation, which is actually on the formula sheet, specifically written this way. U equals U prime plus V over 1 plus U prime times V over C squared. So now, this is the relativistic addition of velocities. Okay. In this equation, the way that it is written, U prime can be defined as the velocity of the moving, you can call it a frame of reference formally in physics, but you can just replace it by the term point of view. Okay. V is defined as the velocity and object. That object can be anything, including light itself, moves in that same point of view. Okay, so let's say that it's a person on a skateboard, right? You have a skateboard. This is the moving frame of reference, or the moving point of view. So there's a person attached to the skateboard. They don't see their skateboard as moving. Okay, so, but if you treat this as one system, the whole frame or point of view is moving with 0.5 c. Now, they have, in this case, a flashlight, which shines light out with a speed c. okay, and it's in the direction of motion. So this would be your velocity that's in that same point of view. This would be v. Okay, so v is equal to c, and this here is u prime. U prime is equal to 0.5 c. So then the velocity u is the velocity you observe outside that point of view. Okay, so u is defined as the velocity outside that moving point of view. Okay, so there's a person standing off to the side here, and they watch this whole thing move to the right. From that point of view, they measure the velocity u, which is the answer that you get for this. So it turns out that in here, if you plug in the appropriate values of c and 0.5 c, you plug it into here and here, here and here, the answer for u that you're going to get is still actually 1.00 times c. So, but in any case, even if you didn't have a beam of light where the answer is obviously going to be c no matter what you do, if you have something that's moving less than the speed of light, so like 0.7 c and then this is 0.5 c, you still plug them both into the equation and you'll get an answer which is less than c. Okay? It's not going to add to 0.5 plus 0.7. It's not going to give you 1.2, obviously. Now, the other thing to account for, to be careful about, is that these are velocities. Velocities have direction. You can move in the positive direction and you can move in the negative direction. So, for instance, something that's moving to the right is written as a positive number. But if I were to, for instance, throw something backwards, then I would write it with the negative number. So if I took an object and I threw it this way at 0.7 c, I would write it as minus 0.7 c, and that's what I would plug in to here. So you would end up subtracting something rather than adding something. Okay. So that's a little bit more general. You didn't need all of this to solve this problem because the answer was just c, but if you changed it to a problem in which you added some velocities together, this is what you would do. Okay. This section really confuses me too, so don't worry about it. I've probably spent a number of years being confused about this entire chapter, which it still has confusions even to this day. So if you're confused, you're not alone. So answer for that was just letter C. 10. An astronaut leaves Earth and goes on a journey which takes 20 years to complete according to themselves. In other words, according to the astronaut, they measure 20 years. From the perspective of someone on Earth, so from their point of view, someone else, they see the astronaut moving with a velocity of 75% the speed of light away from Earth. How much time has elapsed according to the observer on Earth? This is an example of time dilation. So you're going to pull out the time dilation equation. Now you need to determine who is who in the equation. So for example, you have the Earth, so here's the Earth, and on the Earth you have someone, some observer, and there's a spaceship somewhere out here, and there's a person on the spaceship. This is the astronaut here, and they have a clock in their hands that keeps track of time, and according to the astronaut who looks at the clock that they're holding, they say that it takes 20 years to make whatever journey they're doing. Okay. Now, the clock is measured by the astronaut, so they have the clock that they're holding. The time dilation equation states that there is some time that's measured, which is based on what's called the rest time, delta T naught. And it has the following definition, is that delta T naught, also known as the rest time, is the time measured by someone who sees the quote-unquote clock at rest. Okay. Delta T is the person who sees the clock moving. So delta T has the same exact definition, but sees clock moving. Okay. Now, with these definitions, you have to ask who sees the clock at rest. So in this case, now you would say, oh, you know, the spaceship is moving, and you would draw a velocity on it, and you would say, oh, okay, so it's 75% the speed of light that's moving away from Earth. Now, the astronaut does not see the spaceship moving. The astronaut thinks they're stationary. So when they look at the clock, they sit in their spaceship and they hold the clock. The clock looks stationary in the perspective of the astronaut. So the 20 years here that the astronaut measures is the rest time. This time here is measured in a point of view where the clock looks at rest. Okay, the astronaut sees the clock at rest. Now, on the other hand, the person standing on the Earth watches the whole thing here. So they watch the entire spaceship with the clock. Okay, they see it moving away from them with some velocity. So V equals 0.75 c, 75% of the speed of light. So in this person's perspective, the person standing on Earth, they see the clock moving somewhere. So this person over here, whatever their answer is, they're going to measure delta T. This person, the astronaut, is measuring delta T naught. Okay. So when I use this equation, once I've identified who's measuring the clock at rest and who's measuring the clock moving, I can then plug into this appropriately. So in this case, I don't need to solve this because it's already solved, because this is the person on Earth measuring the clock moving. So I can say it's going to be a time of 20 years divided by this factor on the bottom, which is 1 minus 0.75 c divided by c. So the c's just cancel, you see? And then square that. Now, you can calculate the bottom separately if you want to. You can calculate gamma if you want to, or you can just throw it all in at once. It turns out that if you do calculate gamma, which is 1 over the bottom, it ends up being about roughly 1.5. Okay? So then what happens is it's 1.5 times 20, which ends up being approximately 30 years. Okay. So the person on Earth measures that it takes more time to do the same thing. So the astronaut would appear younger than the person on Earth. Let me know if you have any questions on the time dilation before we look at the next problem, which is very related to this one, which is length contraction. c is the speed of the light. C is the speed of light. 0.75 c therefore means 75% of the speed of light. Cool. All right. This problem is actually pretty much the same context, except I'm using distances and not time. Where did that equation come from? It's the time dilation equation. So that's the time measured by any particular observer depending on their circumstance. When something moves at a very good appreciable fraction of the speed of light. So it's the time dilation equation. I'm not sure if that was what you were looking for, if you're looking for something else about that. I'm going to do problem 11, but so instead of gamma, you change it to time. So actually, let me write it this way. So the way that you can write this equation to mean the same thing is that you can take 1 over the square root of all that and call it gamma. So this is gamma. If you take this and you multiply it to delta t naught, it'll be the same thing. So in other words, therefore delta t is equal to gamma times t naught. So this is the shortened down version of this equation here. It's the same thing, but written with gamma. That's all it is. So let me know if that makes it a little bit more clear with that. We're going to do the same thing with the length contraction equation, but that's essentially what it is. So I think on your formula sheet, it is actually written that way. Yeah. So on your formula sheet, the time dilation equation actually has it written this way, where they give you this. So this is just how it expands out when you put it all together. But yeah, otherwise you're given these two things over here. So. Okay, cool. Glad you got it. So when you use it on the test, that's exactly what it is. For 11, you have the distance between Earth and a nearby star, which is measured to be 100 light years is what that abbreviates to. Now, it turns out you don't even need to know what a light year is for this problem to solve it. But a light year is the distance that light travels in 1 year. So if you take the speed of light, which is c, which is 3 times 10 to the 8th, and you multiply that speed of light to whatever 1 year is in seconds, that distance in meters is 1 light year. So it's a very, very, very large distance, but we are abbreviating it as LY for light year. Whatever that distance is measured by an astronaut who is traveling between Earth and the star. The person on Earth sees the astronaut traveling with a velocity which is 75% of the speed of light, which is why I'm saying that this is pretty much the same as the last problem, because I'm also doing it with 75% of the speed of light, but I'm doing it with distances and not time. So this one's time dilation, the next one's length contraction. So if you calculated gamma from the previous question, you can reuse the same gamma because it's the same speed. So the person on Earth sees the astronaut traveling with that velocity away from Earth and measures what distance to the star. So I'm asking what is the distance to the star from Earth according to the person on Earth, not the astronaut. 100 light years for the distance between Earth and the star is measured by the astronaut, not the person on Earth. So in this setup here, I'm literally going to have the same exact setup here. I'm just going to erase the details about the time. So now, I'm not going to care about the clock anymore. Now, there's a star somewhere to the right of this picture. Say this is my star. Okay. So here's a star, something kind of like our sun, but a different star. Now, there is a distance between here, the Earth, and the star. Okay. Whatever this distance is relative to who is measuring it. So for instance, I'm telling you that the astronaut measures that distance to be 100 light years, LY. Okay. So according to the astronaut, it's 100 light years between the Earth and the star. Now, my question is, what does the person on Earth say that distance is? So you have a length contraction problem where I'll write it this way first. L equals L naught divided by gamma. That's the shortened down version of that formula. With gamma plugged in appropriately, you get the square root of 1 minus v over c squared times L naught. Okay. So that's how it expands out. Now, L naught and L have a very similar definition. So L naught is called the rest length, which is defined as the length measured by someone who sees the quote-unquote length at rest. Okay. L is the distance measured by someone who sees the length moving. So the non-rest length, also known as the proper length, same exact wording, but the wording in the end is sees the length moving. Okay. So in this picture, the way I want you to see it is, so let me bring out my tape measure again. Let's do this. Okay. So here is this, this gigantic length that spans from the Earth to the star, which is many, many light years away, and it would take your lifetime to reach. Now, this distance, depending on whose perspective you ask for, will either be stationary or the length will move. So, for instance, for the person on Earth, let me do it this way. Okay, so for the person on Earth, they do not move relative to the star at all. So in other words, when this person looks at this length right here, they don't see the length moving. So therefore, they measure the rest length, L naught. Okay, so I'm claiming that this will be L naught, whatever they measure. Now, if you ask the astronaut what they're seeing, you have this length here, but as this person in the spaceship travels to the right in this diagram, now keep in mind that if you ask the astronaut, say that 10 times fast, if they think they're moving, well, then they're going to say no, everything else is moving around them. So as they move to the right in this diagram, if you were to put yourself in their perspective, they would see this length drifting to the left as you would think they're moving to the right. So this person starts at Earth, they see the whole length in front of them. But as the astronaut travels to the right in this diagram, it looks like the length is traveling to the left behind them. They're leaving it behind. So by the time the astronaut arrives at the star, the entire length will be behind them. So they measure the non-rest length. So ask the astronaut. They measure L. Okay, so they take the L. So now that you've identified who's the rest length and who's the non-rest length, now you can use the equation properly. So in my case, I want to know what the person on Earth is measuring. So it's L naught that I'm solving for. So from this equation, I need to solve for L naught, which is equal to L divided by the square root of 1 minus V over C squared. So now, when you plug in the appropriate numbers, you get, so the length L measured by the astronaut is 100 light years. And you divide it by whatever all the stuff in the square root ends up being. L naught will be larger than L. It turns out that L naught will be around 150 light years. Okay, so the person on Earth measures the distance to the star to be 150 light years, while the astronaut thinks it's shorter, or contracted, 100 light years. Let me know if you have any questions on how the lengths are assigned to each person's perspective and how you end up solving that from there. Oh, you looked it up. 1 light year equals 9.5 roughly times 10 to the 12th kilometers. Yeah. In other words, that is a trillion, 10 trillion kilometers almost. So for the sake of completing the joke earlier about the astronaut taking the length L, the astronaut also goes to the star and returns back home, so they do also bounce back home. But anyway, so this problem and the previous one are done the same way. We just use T for time and length for L. Yeah, kind of in a way, because all you're doing is you're assigning who sees something at rest and who sees something moving. The equations are only subtly different than each other. So in one case you have time dilation, meaning the time gets larger for one person, the person that you see moving. And in the other scenario, the person who's moving that you see will have their length appear contracted. So it's very similarly done to each other. 151. Yeah, so it should be 151, which is... in here, it's the answer B. All right. Let's see. Let's look at number 12. This one, I'm going to write the equation. I'm going to tell you what the answer is to speed it up a little bit. The observed peak frequency of light emitted by the sun is estimated to be this frequency here. What is the approximate temperature of the surface of the sun? Here, you have to make the connection that the sun is treated as a black body in physics, which means that you're going to talk about blackbody radiation. There is one very simple equation that we use for that on your formula sheet. I actually just verbally mentioned it. So if you look at the quantum physics topic, which is Weins Law, you have a frequency peak, which is some constant times the temperature of the blackbody. In this case, you know the frequency peak. I give it to you. It's 3.41 times 10 to the 14th hertz here. And you only are missing T. So when you divide off by that constant, you get T, and you're going to find it to be 5,800 Kelvin. That'll be it. Okay. So that's all you need to do for that one. For 13, the approximate size of the hydrogen atom out to the first orbital is on the order of 10 to the minus 10th meters. If the electron has a de Broglie wavelength on the same order of magnitude, in other words, roughly, again, 10 to the minus 10th meters, so if it has that de Broglie wavelength, what do you expect to happen when the electrons are sent through a double slit setup based on this conclusion? So what you should get out of the de Broglie wavelength was that when the de Broglie wavelength of whatever thing you're talking about is around the same order or smaller than the hydrogen atom size, which is around 10 to the minus 10th meters, it behaves more like a wave. And if the de Broglie wavelength is larger than that value, then it behaves more like a particle. So based on this conclusion, I would say that the electron behaves more like a wave. So if you send the electrons through a double slit setup and the electron behaves more like a wave, then what do you expect to happen? So remember that the double slit setup showed that light behaves like a wave when you send it through two slits because you don't get two bright spots. You get tons of bright spots. Bright, dark, bright, dark, bright, dark. The same thing is going to happen to the electrons if you send them through your double slit setup, given that it behaves more like a wave. So the answer to this is that you will get a pattern of numerous dense and less dense spots with electrons that will appear on your viewing screen. The answer you might have expected would be that there'd be two areas of densely packed electrons on the screen, kind of like there'd be two bright spots, but that's if it behaves like a particle. So in that case, we're saying that it behaves more like a wave. So electrons actually will create a very similar pattern to if you were to just shine light through the two slits. So I'm going to continue trying to go forward so we can finish this a little bit faster because it's about 11 o'clock now. So drop any questions you have along the way as we go through this. 14 is this... 14 is a problem which is on the photoelectric effect. You are given a wavelength of light that you shine onto a sheet of platinum, which is really, really, really expensive, by the way. We would not give you that in a lab. It has a work function of 6.35 electron volts, and I want to know what the maximum kinetic energy that the electrons get. So for this, you simply take the equation that you have for the photoelectric effect. So on the photoelectric effect, you have that the energy associated with the electrons, also written as K maximum, equals HF minus W naught. Now, I'm very simply asking you for what the maximum kinetic energy is, so you don't need to do anything with this. You just need to plug the numbers in and calculate what that is. So F is the frequency of the light that you're shining, but I give you the wavelength. So in other words, you need to convert the wavelength to a frequency first. So you need to say the wavelength equals C divided by F. You can make that calculation real quick. Speed of light divided by, solve for the frequency, not the wavelength. So divide by the wavelength, which is 243 nanometers. And you get a frequency of light that you're shining to be 3, 10 to the minus 9th, in the bottom, multiply 3, 10 to the 8th. So you get 1.23 times 10 to the 15th hertz. The precise number is 1.2345678 9, so a little funny. You get that there. That's the frequency you plug into here. Now, I would advise you that because on these formula sheets you do have Planck's constant in terms of both joules and electron volts, I would highly advise you to use the one that has electron volts in it already so you don't need to do the conversion yourself. So, in other words, you should plug in Planck's constant as a value of 4.136 times 10 to the minus 15th electron volts times seconds instead of joules times seconds. So we're doing this because the work function is normally given in electron volts, which in our case it is. So we subtract off the given value of electron volts for the work function for platinum, which is 6.35 electron volts. Now, if you run this calculation here, you plug this in, times the frequency, forgot to multiply by the frequency, so you take that and multiply by the frequency. Okay, so you get some amount of electron volts and you subtract off 6.35. Now, the thing that you're going to quickly realize in doing that is that this term right here, this term, has to be greater than the work function conceptually, because the work function is the energy required to get it to start ejecting electrons. This term is the energy you're putting into it. The thing is that if you make a calculation for this in this problem, I'm going to tell you right now that this number is less than 6.35 electron volts, okay? Because this number right here is already less than 6.35 electron volts, you know that you do not have the energy to overcome what is needed to eject the electrons. So when you do some number that is less than 6.35 and you subtract off a number that's bigger, 6.35, you're going to get a negative value. You can't have a kinetic energy which is negative. The lowest value it can be is 0. So in other words, therefore, the energy, or Kmax, is just 0. That's it. They do not eject. Okay. So that's it. So the energy is 0 for that. They do not eject, period. We're going to keep on moving forward. Drop any questions you have on that or anything else I've done. We're approaching the end of these now, so this will be the last topic in here, which is on the hydrogen atom and the electron states. Number 14 is B, that is correct. 0 electron volts. For 15, this is a hydrogen gas and spectrum that you observe. You observe ultraviolet light corresponding to the highest possible energy level transition to n equals 2. What is the wavelength of this light that's observed? So we're saying that we have an energy transition in the hydrogen atom. You should automatically say it's the Rydberg equation. Now, in the Rydberg equation, you can do many things with your energy transitions from one state to another for the electron. However, in this particular case, I am telling you two things. I am telling you that the transition goes to n equals 2, so it ends up at n equals 2. The other thing I'm telling you is that it's the largest possible transition that you can do in this setup. So in that case, we have that when you use the Rydberg equation, 1 over n prime squared minus 1 over n squared. we know that n prime has to be 2 because that's the energy level that you go to, and that has to be a lower energy state. So n prime equals 2. This is also characteristic of a series that we call the Balmer series. The n level is the energy level that you start at, but I don't hand it to you immediately. I tell you, though, that the energy transition is the largest possible, which means that you keep on going up in the energy level until you hit the maximum, but there is no maximum, it's infinity. So n goes to infinity for largest energy transition possible. Okay. 1 divided by a ridiculously large number ends up being 0. So in this case, this term ends up dropping out because it's approximately 0. So really you just calculate this part, and you don't forget to invert this so it's lambda. So in solving for that, you'll get the following answer. Lambda is 365 nanometers. And this is roughly UV light if you want the part of your electromagnetic spectrum. Alternatively, if I asked you another question, which is what's the smallest energy transition possible, instead of infinity, it would have been 3, which is the next one up from 2. But the largest energy transition possible is always going to be from infinity down to whatever you want to do for the other one. How do you know n prime is 2 instead of n? That's because the definition is that n prime is defined as the final energy level, and n is defined as the initial energy level. And the thing is that when you go from a low energy state to a high energy state, which is not what you're doing here, when you go from a low energy state to a higher energy state, you have to take in energy, not release it. And light is a form of energy. So if you see light emitting from something, that means it's releasing energy. So in order to release energy, you have to go from a higher energy state to a lower energy state. So that can only mean that the n value must be bigger than the n prime value. So n must be greater than n prime as electron goes from high energy to low energy state and releases. The key term is release. Releases energy in the form of light. So conceptually, that's why that has to be true. But otherwise, n is the initial and n prime is the final, and it has to be that way. You'll notice that if you actually flip them, you get a negative number, and you can't have a negative wavelength. So that's how you'll also know mathematically that it can't be the other way around also. Okay. Let's look at the last two problems on here. These last two problems are very closely related. This has to do with the configuration. So here, how many 4p electron states can there be? Another way I could ask this is how many possible configurations could I have? So there's two things you should pull out of this 4p. First has to do with the number that's in front, and the second has to do with the p that's in front, or whatever letter it ends up being. So for 4p, in our case, the first number represents the energy level. Okay. The energy level, I believe it's also known as the principal quantum number. It's just your n value, which is in this case 4. The P has to do with SPDF and the orbitals. So SPDF. There's more than F. It's also G and H, I think, but we're going to focus on SPDF. But for SPDF, they each correspond to the following. L equals either 0, 1, 2, or 3. Okay. So they're telling you the L value when they give you S, P, D, or F. So in our case, P, so this implies P gives us L equal to 1. Okay. So essentially, by giving you the 4p state, I'm just telling you that n equals 4 and L is equal to 1. Now, from here, I want you to tell me the number of configurations that I can have that follow this condition, or, as I said, how many electron states can there be. So there are a few rules you want to remember, is that for some n value, if you'll have the following be true, your L values will range from 0 to n minus 1. Okay, that's the range. Okay, and they are, remember that these numbers are quantized, meaning that they're all set amounts. They're not going to be, it's not going to be a gradient. So you can't have like 0.5 and 1.2 and all those numbers in between. This is assuming you're counting by integers. So in this case, 0, 1, 2, 3, 4, just counting by whole numbers up to whatever n minus 1 is. The m sub L value equals, and it's based on the following range, is minus L to positive L, also integers only. So integers only and integers only. Okay. So the range is minus the value of L that you choose to whatever the value of L is. Finally, m sub s is either plus or minus a half. That's it. Okay. So now what we're going to do is we're going to take this 4p and we're going to generate all of the possible states that we can have. So for instance, as you make a table, so we have n, L, m sub L, and m sub s, like that. I'm letting n be 4, that's set in the problem, so n is 4. I am setting the L value to 1, so 1. These are set in stone, they're not changing in this problem. The m sub L, it can be a whole range, because we said m sub L could be anywhere between negative L and positive L. But in my case, L is 1. So it could be negative 1 to positive 1. Now, what I'm going to do is I'm going to start with the lowest possible value first, and we're going to go in orderly manner. So for instance, m sub L being negative 1, I can have spin up or spin down, which is plus or minus a half. Now, I'm done with negative 1, so I go to the next combination, which is 0. For m sub L equal to 0, I can also have spin up, spin down, or plus or minus a half. And finally, I can have positive 1 for m sub L, because it can go to positive 1 as it could go to negative 1. And also I'll have plus or minus a half on that too. And those are all the possible combinations that you can use for m sub L, given that this is your L value. I could make the problem so that I could consider also L equals 0 if I wanted to, but in this problem we're only considering L equals 1. So how many combinations do I have? Well, each one I've listed is plus and minus, so there's 2 combinations per line. So we have 2, 4, 6 combinations. So therefore, 6 possible states. So that's the answer to that. And the answer for that ends up being D for 16. And I'm going to do the last one since we're here, and then I'll answer any last questions on all of this, and then we'll call it a night. So on the last one here, we have what is the total angular momentum for the 4-piece electron state, which is exactly the same one we just did. So the total angular momentum for that is just going to be capital L, the angular momentum, equals the square root of lowercase l, l plus 1, times h bar, where h bar is h divided by 2 pi. We're not going to need to do that though, because we're going to leave it in terms of h bar to match the answer. So all I want to do is say, for the 4p state, well, p means that l is equal to 1, so I plug in 1, and I have 1 times 1 plus 1 times h bar, which ends up being 1 times 2, which is the square root of 2, h bar. But that square root of 2 is just 1.41, and then times h bar. So the total angular momentum for that state is 1.41 h bar. So the answer to 16 was D. And the answer to 17, the last one, is 1.41 h bar. Okay. Are there any last questions on these remaining questions? And then we'll go from there. If everything is good, let me know. What does M sub s stand for again? It is the spin of the electron. So particularly it's spin up or spin down, represented by plus a half and minus a half. Show the board real fast. Okay, yeah, we're good now. No problem. Looks like we're relatively good. All right, anytime. I think we are good. So with that, so tomorrow night, same time. I'm going to see if I should dial it back a little bit from 9 o'clock. I'll see. I'll let you know if I'm going to do it any earlier than 9 o'clock. But for now, assume it's at 9 o'clock tomorrow. Same link, because I gave you a link that works universally regardless of which live stream you're doing. However, if you want to re-watch this particular live stream, you cannot just go back to the same link. So what you're going to do is, either 3 hours from now or tomorrow morning, whenever it gets uploaded by, you'll go to my channel and you'll go under the videos tab and you'll see the live stream there, and you'll just rewatch this live stream if you need to. You can fast forward it if you want to, whatever you like. And then tomorrow we'll come back to the same link that you came to today. On the Canvas page, I linked that, and then we're going to do the same thing. We're going to go over a second version though, and I'm going to kind of mix in a couple more concepts into that we may have kind of skimmed over, and maybe I'll take out a couple of the single or double slit problems that we had a lot more of, to kind of balance that. So we'll do a little bit more relativity, we'll do a little bit more of the quantum stuff, so we can balance it out a little bit better and get a better feel for that. And we'll go from tomorrow. Otherwise, the in-person review session will be on Wednesday with the details listed on the Canvas as well. So with that, thank you for tuning in, of course. And if you like what I've done, especially as we're approaching the end of the semester and you're going to be done with this class in physics, if you like what I do, let others know. Anybody else who's taking physics, any of your friends, let them know. And it kind of gets my name out there to other people, and especially if you're taking like the MCAT. If you know anyone else taking the MCAT, reach out to me. I'm happy to help out in any way I can. So with that, thank you for watching, and we'll catch up tomorrow. Have a wonderful night.